So, hey everyone, I'm Shaista Fatima. I'm going to be your host today, and we are presenting differentially private model training with Opacus, presented by Davide Testuggine, and he is the applied research scientist at Facebook AI. And it's great to have you all here. Thank you for joining us today. Just before we begin the session, I would like to go with a general housekeeping, like quick 2 seconds. General housekeeping. All the participants are muted by default. Only panelists will be able to speak. If anyone has general questions, they can ask them in the Zoom chat. If anyone has a question regarding the live tutorial, ask it in a Q&A box. Participants can upvote questions, that is thumbs up. And in the Q&A box, the questions with higher upvotes will be answered first because of the time limit we have. And just like a second ago, just give me a thumbs up. Can you guys type a B if you can hear me perfectly and if you can see the screen properly? Okay. Okay. Looks like everyone can see it. So over to you,
Excellent.
David.
All righty. Thanks for the introduction. All right. So in the time we have together today, we are going to cover quite a bit of ground. So we're going to talk about DPSGD. So we're going to talk about how you can train deep learning models with differential privacy. And in case someone is not fully familiar with differential privacy, that's entirely fine. We're going to cover some of the bases to what pertains DPSGD. We're going to have some pointers in case you want to dive deeper, but we're going to stick to kind of like the bare minimum to keep the flow going and don't bore anybody else. Then we're going to talk about training models with DPSGD, both like kind of like the theory behind it as well as the practice. So there's kind of like a few caveats that you might want to know before you kind of like do it in practice. Some of these caveats we kind of like built some helpers in Opacus. So we're going to go over a quick tour of what we've built in there. And then finally, we'll turn over to Colab and play a bit with it. All righty. So to introduce differential privacy to you, I'd like to start from an example rather than a definition. And the example is very, very simple, but it will allow us to develop some of the key intuitions that we're going to use here. So imagine you're something like a hospital, and you're looking into counting something like how many smokers there are. You may care about this because you want to allocate resources, you want to have more beds, buy more machines, what have you. On the other hand, though, the people that you want to ask it to may not want to answer that. What if you tell on them and let their insurance know? Maybe they get an insurance hike. So they want to have some sort of privacy protection into their answer. And so how do we do this? How do we kind of like still see the forest, but somehow lose some resolution on the trees? The answer is remarkably simple. You just ask them to flip a coin. If the coin should come out as heads, of course, you won't see the result of the coin, but if it comes out as heads, then they will answer honestly. And if it comes out as tails, they'll say that they are smokers, whether they are actually smokers or not. And so what does this accomplish for us? So imagine we have thousands of them. And let's say you run all of these shenanigans, and these are the answers that come out. We know that these don't mean that 65% of your population is made of smokers. Why? Because we know that 500 were just due to the coin landing on tails. This, of course, means that 500 of your answers weren't really honest in general, so we can discount them. And this leads us to kind of like estimation of what the real number was, so 30%. And the interesting bit about this is, what if we pause now and think about what happens if somebody has given you a yes and you see a yes? Does that mean that they're a smoker? Actually, no. The probability that they are a smoker is remarkably smaller than them having just answered yes due to chance. And so this provides them with, what is being called plausible deniability. Like they can, they have a good answer when you ask them, why did you say yes? Well, probably because of that. So this is not differential privacy, but it has, and this is in fact called randomized response and comes all the way from the 60s. But it has some seeds that differential privacy is kind of like built on top of, and allows us to, first of all, generalize much more. Like in this case, we only have one coin at our disposal. It's you can imagine that we could control the bias of the coin to provide more or less plausible deniability. Here, we're also protecting the privacy of one of the answers. Of course, them telling you no is not something that they may feel embarrassed about or worried about, but there are other circumstances where, of course, maybe also the negative answer needs privacy protection. And of course, this is only one bit of information. What if you want to do more bits? Now this becomes more and more complex. And we can address this with differential privacy. We're going to go over the formula, but before we do that, let's just start with kind of like a key intuition. One of the things that are amazing about differential privacy is how general it is. So this definition literally says, imagine there's a data set, can be anything. It goes into an algorithm, can also be anything. It can be as dumb as counting stuff, or as complex as training a deep learning model. Doesn't matter. Whatever it does, it will produce an output. Now, the key idea behind differential privacy is to imagine a mental experiment where I take some data set and I construct another data set, which is exactly the same, plus one record, my data, one row of my data. Let's call this data set D prime. This data set will also go through the same algo, and it will produce a different result. All the differential privacy is saying is essentially that these two results should be almost the same. That makes sense, right? If anything, like if the inclusion of my data, let's say you have a data set with like 1 million rows, and the inclusion of my data makes it 1 million plus 1 and makes the output change significantly, then there's probably something wrong about how much information it's extracting from my data sample. To be more precise, almost the same is a good intuition, but let's be a little bit more precise here and just say similarly distributed. So we're gonna make kind of like a probabilistic take on this. So let's look at the formula now. And the formula is gonna tell you exactly the same thing as before. This is exactly the same thing. Two data sets are adjacent if they differ by at most one record. So these would be the black and the orange one. And this is a guarantee that operates on probability distributions. And since it's a guarantee, it's by definition dealing with worst case scenarios. So what's the worst case scenario here? Let's enumerate all of the possible events that can happen. And what we're looking for is checking the event for which the probability of that event occurring changes the most. So for example, if your algorithm is like counting and you're counting people with a certain name, if you count the Johns and you include my data, the count for the Johns won't change. My name is not John. So that's kind of like a best case scenario. But if you count the Davides, then it will change. So you may be able to find whether you are looking at D or D prime. And so in these cases, what differential privacy is saying is that no probability is allowed to be changed by more than e to the epsilon. And epsilon is a parameter, or what people call the privacy loss budget. It's a budget, but it could be a bit counterintuitive that actually the higher the epsilon, the more these probabilities are allowed to diverge. Therefore, the less private this is all this whole thing is. So actually, you want epsilon to be small. It's not though like a random parameter. It actually has a precise meaning. If we know epsilon equals 1, it means that the probabilities are not allowed to change by more than e to the 1. In DPSGD, we're also dealing with the epsilon delta definition of differential privacy, which includes a small probability of failure. We're not going to go over details about this one today, but essentially it extends the applicability of differential privacy considerably. As an engineer, there are two properties of differential privacy that I find particularly exciting because it makes differential privacy very, very easy and very, very nice to work with. One of them is composition, and the other one is robustness to post-processing. So for composition, the idea is that, let's take a look at this again. We have a result, and now we know that this result, if we did our job right with our coin tosses and whatnot, is going to be differentially private. But what happens if we are allowed to repeat the experiment again? So if we repeat the experiment again, there's going to be other coins tossed, or more in general, other noise added. But the more you do this, the more these will tend to cancel out. So you might be able to find more information. Right? Differential privacy is kind of like being putting itself between the data and your query. And if you're allowed to query continuously, you will eventually break it. So the privacy, so one question is, what would be the new privacy budget if we group these two as kind of like a single mechanism? What's the cost of that? And the answer is, again, remarkably simple. You just sum the epsilons and you sum the deltas. So this allows us to analyze repeated applications of this. So this is one case where somebody is looking at the data continuously or multiple times. The other property deals with an adversary who doesn't look at the data ever again. They're not allowed to, but maybe they're thinking very, very hard about breaking it, right? And they're calling all their smart friends. So what can they do, if they try to reverse engineer and break this epsilon just by looking at the result? Maybe there's some very smart post-processing that they can do. Well, this property says that actually they will be out of luck. So this property makes it very, very nice to work with DP on, for example, pipelines. Because if you gate where the access to the data is, and you put differential privacy mechanisms in there, everything else downstream is going to be protected as long as there are no more accesses to the data. If there are, we use the first property, composition, and we can compute the new privacy guarantee. With all this out of the way, let's talk about the DSGD algorithm. So let's do this again. We've seen these icons before. So if we are in, for example, PyTorch land, data can just be a data set, for example, one from Torch Vision. What about the algorithm? So the DSGD deals with private training. So our algorithm is actually going to be training a machine learning model. If you have played with PyTorch or TensorFlow before, you have probably written many of these. And finally, if that is our algorithm, what's our output? That has to be a trained model. So a model with all of its trained weights. And change any one of these numbers here, and you would get a different result. And so now, if we have two different results, these are really two different sets of weights, and they have to be similarly distributed. And I'll make a short break here to make a point that this is why it also helps to say similarly distributed rather than almost the same, because almost the same wouldn't really work for us here. Think about how much, for example, deep learning models depend on initialization. You need to set the same random seed to get to the same model on the same data. Even if you keep the data set the same and you change the random seed, you may end up with very different sets, a very different set of weights. So what we're saying here is not that the set of weight, the particular set of weight has to be exactly the same. We're saying that the probability of any of them occurring shouldn't change by too much. So differential privacy is a definition. It's not a technology, meaning it doesn't really do anything for us. It will only certify that you did a good job. So again, to go back at our example, we had to come up with the idea of tossing a coin and kind of like having our scheme to protect people's privacy. Once we've done that, we can use differential privacy to analyze it and to say, hey, actually, yes, this warrants the differential privacy badge or not. So it will be up to us to do it here as well. So what do we do? Well, we need to find where we are connected to the data in our algorithm and change that. And where we are connected to the data is right here. These are the gradients of the loss with respect to your parameters. And they depend on your data, well, I guess indirectly via the loss, right? So the loss is computed from your model, the application of your model on X, so it depends on X. And of course, it takes the labels Y. So the plan here is to, instead of tossing coins, they're heavy and annoying, we're gonna instead sample noise from a Gaussian distribution. It will have zero mean, and we can, of course, this is a Gaussian, so we will have to set the variance ourselves. Now, normally people like to think more in terms of what epsilon and delta they're targeting, but this is parameterized by sigma, so we're gonna need some math, and somebody else did that for us, and you can pick sigma so that you can get whatever epsilon and delta you want. Great, so with that out of the way, now all we have to do is to apply it in practice. So let's go back to our training loop. And this is the training loop as we left it before. And now we want to sprinkle our differential private magic on it. And all we have to do is to intervene on the gradients as we discussed. And so we're going to sample from a normal distribution. We're going to add it to the gradients. And then the optimizer can go back and kind of like do its job. Here's an important take. One of the things to like about differentially private model training is that whenever you're done with all of your training, your model will satisfy DP thanks to post-processing. So you can, for example, run however many queries on it as you want. You can have multiple predictions from it, and it will still be differentially private. This is an advantage that the system has, as opposed to, say, private prediction, where instead you place a differentially private mechanism to gate the model's predictions. You can do that, but then you have to be careful in how often you query it, because then you have to apply composition rule and change your privacy epsilons. Speaking of composition, composition also carries a cost for us. So I've been talking about the cost for private prediction, but it has a cost here as well. And the cost here is that we are applying this privacy, this Gaussian mechanism upon every batch, right? So batch comes in, we train it with the usual algorithm, right? For each batch in the training set. So one batch comes in and we do it, and we're gonna pay epsilon for it. Next batch comes in, so we're gonna pay another epsilon here, and so on and so forth. So here we need to be careful that every single batch is gonna cost us something. In particular here, if we use the kind of like standard composition, we're gonna pay epsilon delta for each batch, which can lead to pretty humongous privacy epsilons, which don't do all that much. So that would be an area of improvement, but apart from that, we're done. So thank you very much, and I will take questions. I lied. Yeah, if it was this simple, we wouldn't have written a library for it. The problem is the gradients in a batch are unbounded. And so this makes your life significantly harder. Why? Well, let's take a look at a single, let's say we train, like we do like a gradient computation from a loss for a single batch. And let's say we look at each of the samples in a batch. So in this case, we have a batch size of 8. So we're gonna have 8 of these. And let's say we look at them individually and we see how big the gradient is, like the norm of the gradient for each of these samples. And we can see that one of them is disproportionately bigger than everybody else. Let's also see them unstacked. So what's happening here is, of course, that maybe we aren't learning much from number 0 because we got it right almost already, right? So with cross entropy, we get penalized for our confidence. So maybe we said maybe this is like a binary classification problem, and we said this is a positive with 95% confidence, and this was indeed a positive, so we just get penalized for not having said 100%, so it's very small. And for something like number 6, maybe we were very, very confident it was a negative, and indeed it was a positive, and so we gotta pay the price. So there's no way to bound these. These can be like even more skewed and even more extreme. And so now the problem with this is that we are having a very tough time with this in finding the right amount of noise here, right? So if I say chose the second one in green as my kind of like reference, I could dimension my noise so that it's good enough that it doesn't destroy signal for it and it protects its privacy. It can work for the second one, but it will never work for number 6. Number 6 is way too big. And of course, if you dimension it on number 6, I will be destroying signal from anybody else. There's even a subtler point here. Not only that, but I would still not be protecting the privacy of number 6. Why? Because by dimensioning it on the biggest of the batch, I would know that this batch contains an outlier, right? And so if I'm an adversary, I would be obtaining some extra piece of information here. So we need to find a way of fixing both of these. What do we do? Again, the solution is actually remarkably simple. We just flip it. Boom. So in this case, we set a creep iteration of 1.5. So anything that's bigger than 1.5 gets set back to 1.5. And now this is much better. Now we're able to, first, we're able to choose the height of this Gaussian a priori. We don't need to know what's in the batch. And we know that it will reasonably not destroy the signal of our samples. Yes, it may be masking, say, sample number 0, but we weren't going to learn much from it anyway, so it doesn't really hurt us. So let's look at this as a cooking recipe now. To our road to success is going to go through computing per sample gradients for each of the parameters that we're training, clipping them to a fixed threshold that we set a priori. We can be looking. We aggregate them back, and we add noise. Let me show it to you also in a diagram form. So if this is a standard forward, your batch will go kind of like all together. And in a standard backward, you would be aggregating gradients on the way back to your parameters. Rainbow meaning they're already aggregated. And so here it means you would be losing this piece of information. So we need to recover that. So because with the DSGD, you actually need to keep them separate a little bit longer than that. So these, as you can see, these are the pesky per sample gradients. And one of them is bigger, but just to show you that, you know, with clipping, we bring them all back to the same range. Then we aggregate. Now we're back to a single rainbow arrow. And at this point, we can add noise and update our parameters. One last time, this time we're gonna see it in code. How do I do this in practice in code? Different people may be resonating with different things. This is the code sample as from before. We're gonna add a few more things. So first of all, for the per sample gradients, we're gonna have an inner for loop. Let's go one by one. We're gonna, for each of the samples, compute the gradients, clip them, accumulate them somewhere. And at the end, we're gonna stack them back into a single gradient, add noise, and claim success, plus some bookkeeping. Hooray! We have successfully implemented the DSGD. Therefore, again, it's only a few lines of code, right? You certainly don't need a library for it. So why did we waste everybody's time building one? Well, there's a few more things on the to-do list. This is, however, indeed a correct implementation of the DSGD. There's still work to do. One of them is due to the composition. So the composition rule that I showed you is correct, but it would lead to like humongous 1,000+ epsilons when you train a model, which is essentially akin to saying that you have a scale that whenever you kind of like measure your weight on, it says it's no worse than 1 ton. It's correct, just not very useful. The other thing is, of course, we were doing an inner for loop to go over the samples. That's correct, but it's very slow. Your GPU doesn't like that, and so we will have to find a way to vectorize it. The third principle is something that goes in the security community, where it's best if you don't roll your own security and privacy applications, because it's more convenient to have kind of like applications where there's lots of eyeballs behind that can catch errors and can be constantly maintained and improved. So this is what we set out to do with Opacus. Before we get there, let's talk a little bit more about training models with differential privacy in practice. So there's a few things worth knowing. First off, no batch norm. We hate batch norm here. The second one is that we add a ton of noise. I'm gonna show you how much actually. In a way, I'm honestly surprised that this even works, but it does. And finally, we're gonna talk about what happens when you introduce clipping during training. So the first one, it's batch norm. No, we don't like batch norm here. Let's see why, what it is and what it does and why we don't like it. So let's say you have a batch. Whenever you are normalizing with batch norm, each one of your samples in the batch is going to be normalized based on this formula. And actually the formula is the same for each and every normalization layer, right? It's no rocket science. You just subtract by the mean and divide by the standard deviation. All of the layers do this. The only difference is the mean and the standard deviation over what. So in the case of batch norm is, of course, over every sample in the batch. In the case of something like instance norm, it would be only in the channels of each individual sample. So the reason why we don't like batch norm here is that this dependency on your peers in the batch means that your features, after being normalized by batch norm, will have different values depending on who is in the batch with you. Even if, in theory, the batch isn't really anything meaningful, it's just like random, literally random. So by introducing this dependency, the privacy of X with 0 now would be essentially compromised or violated by all of its peers in a batch, and so on and so forth. Of course, all of them have this problem. And so this would have to be analyzed, and this would have to be also, we would have to put like a differentially private mechanism in there as well. We just don't think it's very worth it, considering that only batch norm has this issue. So you could just replace it with something else. Now, the second thing was trying to give you an idea of exactly how much noise we're adding here. So the tensor that you see here is entirely unremarkable. I generated it with torch random. The only important thing you should know about it is that its L2 norm is 1.0. This is another tensor whose L2 norm is also 1.0. And this tensor's norm and this tensor norm and this tensor norm are also, of course, 1.0. All of them have exactly the same norm. However, when it comes to deciding what's the right amount of noise to mask them, how this mass of 1.0 is distributed across the components actually matters. So in the best case scenario that we see here, where everything is perfectly evenly distributed, then we know that no component is bigger than 0.1768. So we could dimension our noise tensor based on that. And if we, math happens, and indeed the norm of this noise tensor will also be 1.0. I kept the parameter sigma here because if you want to make it bigger or smaller, but it would be 1.0. Now let's look at this one instead. For this one, unfortunately, we don't know where the 1 is. So the only choice is to essentially assume that all of them have 1. And in doing that, we are computing a noise tensor whose norm is now 5.6566, which is indeed more than 5x the amount of noise that we added before. Unfortunately, this is the regime we need to be in, because we make no assumptions about how this norm is distributed. Therefore, we just go with the worst option. And this is actually getting worse the bigger the tensor is. So now I'm going to double the size of the tensor. The values will change, but then, so that the norm stays the same. So the norm of this tensor is still 1.0. And if we repeat the same trick, the norm of the noise tensor is still going to be 1.0 times sigma. And if we double in the worst case scenario, now we're looking at 8. So previously it was like 5.6, and now it's 8x the noise. And of course, the bigger we make it, the more noise we're going to add. So do keep this in mind. Next up is the behavior of clipping during training. This tensor board is coming from Opacus. I'll show you in the demo in a second. Essentially, it's interesting to see what happens and what clipping makes your model do during training. And interestingly enough, the SGD algorithm is able to somewhat adapt to you messing with its gradients and clipping stuff. My mouse doesn't work, but in the diagram on the right, you can see that like the number of layers that get clipped tends to go down up to a certain level. For this particular model, this stays to still around like 0.9, so around 90% of them. In other cases, it can even go lower. So there is some level of adaptation here, and gradients can take quite a bit of abuse and still be able to train a model, which is interesting. So having seen these three phenomena, the tips should be kind of like easy to follow. The first one is, if we don't like patch norm, well, then get rid of it. We recommend group norm. You can also use instance norm. Follow your heart. Just don't use batch norm. The second one is basically about the fact that this noise penalizes largest models the most. And so basically the trick here is to try and avoid training a large model with differential privacy. I'm not saying avoid large models altogether. Of course, you can always train a 2-layer convenant, but then it doesn't do much. But you can use a bigger model for it. Just pre-train it on a non-private data set, Wikipedia, ImageNet, what have you. Then freeze some of it and fine-tune on a few layers. This way you can avoid this kind of like noise trap. And for example, this is something we do in Opacus already. So if you want to replace batch norm with group norm, we got you covered. That function also, you can put a lambda in there and you can convert it to whatever else you want. And for pre-training and fine-tuning, let's look at a ResNet, for example. ResNets are made of these basic blocks, and there's a bunch of them stacked. So each one of them is a conv, batch norm, relu, conv, batch norm, and there's some skip connections in there as well. And that's all there is. So this is a Torch Vision ResNet. It's basically a bunch of basic blocks. Plus, Torch Vision ResNets are pre-trained on ImageNet, so you have an output layer at the end of size 1000. This output layer, you can get rid of it, because unless you want to do ImageNet, you probably are going to have different amounts of classes and you just want to learn it again from scratch. So this one goes away. A good kind of like rule of thumb could be to maybe freeze the first 3 blocks and just fine tune the layers belonging to the final block. This is of course something that you can play with and try. Different models, different data sets will behave differently potentially. And finally, let's go over a tour of Opacus before switching and playing on the Colab a little bit. So this is going back again to the training loop that we saw over and over. So this time though, instead of messing with the training loop, all that Opacus requires you to do is to define a privacy engine here and attach it to the optimizer. That's it. Everything else is gonna work. And if you want to compute your current privacy epsilon, we got you covered as well. So how do we do this? Well, the short story is that under the hood, we basically get notified whenever the model does something and whenever the optimizer does something as well. So to go back to our to-do list, these are the sorts of stuff that we spend some time implementing in Opacus. This is the stuff that maybe you need a library for. We have a rating differential privacy accountant, so we are able to compose the epsilons much better than linearly. So you will not see these 1,000+ epsilons with Opacus. We are providing vectorized per sample gradients, so your code doesn't have to change, and it's also faster. And then finally, of course, we're spending time writing tests and trying to actively break it so that you can trust it whenever, if you decide to work on it or publish a paper on it or whatever. And finally, given that there are some layers that are problematic, it's kind of like very common that you might forget about one pesky batch norm and then it invalidates your entire experiment. So we built some checks into it so that this doesn't happen. Demo time. So I wrote a collab for us. I don't have a second screen here, so I will have to stop sharing, I think, and reshare from the collab. So I'll be right with you. Share screen. Okay. And if you want to follow along, let me also put the URL here. So this is bit.ly 3J8 uppercase Y, uppercase E, 3Q. And of course you can, this will work and you can watch it on your own time, but I will kind of like highlight a couple of things here. But the notebook should run. Some people reported that sometimes it goes out of memory. I try to make it faster by picking the largest amount of memory that I was able to run here. But sometimes Colab gives you a worse GPU. So if that happens, just lower the batch size or try your luck again until you get a better machine. The other caveat here is Colab is still on CUDA 10.1, but PyTorch is on 10.2 by default. So you should install like this. So for now, just use this copy paste, I suppose. Right. So here, let's in this notebook, we're training a CIFAR 10 model with differential privacy. So if you're familiar with Torch Vision, I'm doing pretty standard stuff at this point where we're just instantiating. Maybe we can make it bigger too. Yeah, we're just instantiating data sets and data loaders which will allow us to have iterable batches that we can use. So nothing special here. If you remember, I was saying that ResNets are made of these blocks, and this is one for ResNet 18 indeed. This is layer 1, and it's 2 basic blocks. Layer 2, same thing. So in this code, we are splitting this ResNet into a backbone and a head. And literally all that's happening is basically saying anything beyond up until layer 3 is in the backbone, and everything until layer 3 is in the head. The only difference is that we actually don't want the last piece because it's the ImageNet output layer, remember? So we're gonna throw it away and we're gonna put our own output layer. This CIFAR 10 has 10 classes, so we're gonna put 10. We're gonna keep the backbone in evaluation mode and we're gonna train only the head. This also saves some GPU memory, by the way. This, you're going to apply this model. Basically, this runs without any gradient, and then you just give this model we train. So if we try to go ahead and train it, ooh, your internet connection is unstable. Yikes. Hopefully it works. So let's see. Let's go ahead and train it. Well, I did not run my imports. They gave me a new machine, unfortunately, so I'm going to have to download this stuff again. Shouldn't take too long. I might have to install Opacus again too. Let's see. Yeah, I guess I do. Let's run this thing as well. Sorry, should have run it while I was talking, but it doesn't take long. It's like 30 seconds or so. Indeed, model not found. So by the time this runs, you should be able to see something. There are no open questions, but if in the meantime you have a question on anything so far, we might be able to take them while we wait. Hopefully we're almost done here. All right, this ran. Now we can import. Excellent. And now we should be able to get training. Oh no, error. Damn, error on stage. This must be so embarrassing for the speaker. Well, actually, what the error is saying is that we still have batch rooms in there. So actually, we do want this to throw an error to us. So to fix it, all we need to do is to run our helper, and by doing this, we will magically have group norms in the model that we train. We don't need it in the other one because the other one is not something that we train anyway. So, and now this is indeed going to run. And I wrote a very simple train and test function, not much going on over there. So I'm going to skim over them, and we're able to train. And more importantly, we're able to do this at a similar speed than we would have without differential privacy. Now it's not as fast still, so we're still paying a performance cost, but depending on the application, it varies from like 20% to about half of the speed, depending on how big the model you're trying to train is. But I guess the silver lining is that even if you make it faster, you shouldn't add too much noise anyway. You shouldn't train too big of a model anyway, because then the amount of noise becomes an issue. But we will make it faster still. Yeah, and so, well, these will train for a few more epochs, but I will not run them for you because it will take forever. Interestingly enough, we're already at 60% accuracy with a remarkably small epsilon. So there's kind of like bandwidth for improvement. People train CFAR10 models for like 300 epochs. Here I just trained for 30, and we're pushing 70 at epsilon equals 3. So you can see that indeed, with better privacy accounting, the scaling is much better than linear. The last feature that I wanted to talk about is, I guess, more for researchers or for the curious. The privacy engine allows you to specify a stats function that allows you to kind of like collect stats from a layer. So clipping will be one of the things that interests us the most. We're trying to figure out what it does, when it does it, what's going on. And so in this case, we wrote a function about, kind of like making sure we got all the stats around clipping. And this is supported in the privacy engine. Let's run this again for one more epoch. Now this will go a bit slower because we're logging a ton of stuff into TensorBoard. But whenever this is done, we're gonna be able to learn a little bit more about the algorithm. And of course, this is fully extensible. So if there's something else that you want to log that we haven't thought about, indeed, this is something that you can expand. Almost there, almost there. Launching TensorBoard. Coming right up. Yep, there we go. So this one is literally going parameter by parameter. So we're looking at the bias of the first batch norm. This is why it was so slow. We're looking at the weight tensor of the first batch norm, what's the maximum norm, what's the median norm, and so on. And this is something kind of like something that we just wrote in there, but of course you can change it to whatever you prefer. And yeah, this is important if you're trying to make the DPSGD better as an algorithm. You know, having these logging is something that greatly benefits you. And yeah, that is all I had for the demo. So I would go back to the presentation, and let me change it back to Keynote. Coming right up, sorry. Okay, so to recap, well, this is the same as the agenda. So to recap, we had a quick intro on DP. We saw the DPSGD algorithm. We saw kind of like some tips and tricks and caveats on training models with DP in practice. We had a tour of the Opacus API, and we spent some time on Colab training a differentially private CIFAR10 model from a model pre-trained on ImageNet. If you want more resources, we are writing a blog post series on Medium. The first one is out. We are hard at work on the second one, and we anticipate there are going to be 4 of them. The basic idea is to really try and put everything that we would wish a contributor to Opacus would know to kind of like be effective in their contributions. And so it can be also kind of like a good way on ramping up on differential privacy and on the DPSGD. So, you know, go take a look if this is something that interests you. And the kind of like tutorial that we saw in a notebook is similar to one of the tutorials we have. We have a bunch more on NLP, on vision, and we have also an example on how to train again with differential privacy. So do check out the examples and tutorials in Opacus. The examples are just examples. They just run. Tutorials are also coming with extensive commentary. And yeah, that is all I have. And I'll be taking questions if there are any. Sorry, switching back to Zoom. QA box seems rather empty, so either everyone is fast asleep or it was super clear. So I'm gonna hope it's the second one. Shaista, should we reclaim a few minutes?
Yes, there is a question there.
Oh, there is a question. I see it. Yeah. So hope I don't butcher your name. So it's a question from Ulu Watife. So during the DP definition, you mentioned a new dataset D prime with a new row being added to the previous dataset D. What happens if the number of rows added is more than one? So the kind of like, remember I guess the name differential privacy, we're looking at something like a derivative, right? So why are we, whenever we compute a derivative, why are we looking at kind of like a function computed in a point ever so infinitesimally close to the origin point, right? Why do we look at these small deltas? It's just that so you have a definition for kind of like the smaller unit, and then you can build on top of that. So that's basically just a way of kind of like having a definition that covers this case. You can, another thing that I want to add is that you want to focus on the unit, but the unit can indeed be containing more than one row. We haven't talked about this here, but for example, if you want to protect the privacy of individual examples, because maybe, let's say, every person only contributes one sample, then it makes sense to protect the sample level privacy. If you know that, for example, each person contributes 2 examples, then it does make sense to compute the kind of like per person privacy, and then you will be looking at grouping them first, and then you will be looking at the groups. So it can be more than one. It can be more than one row in that case. This is something that you would do, for example, if you wanted to combine the DSGD with something like federated learning, where you do have a concept of user. Hello again.
Yeah. Hey, looks like we don't have any questions. So anyone, if you have a question, please do ask in the Q&A box. If not, then
or forever stay silent.
1 minute. Yeah. No, don't stay. I mean, I would like you to ask questions if you can. And David, I think, I don't know about others, but I did enjoy this session. So thank you for hosting it for us. And I'll definitely try out the tutorial tomorrow and maybe reach out to you tomorrow. So thank you everyone for joining us today. And if you want, you can just check out these links here. You can join us on Slack if you have further questions. Maybe you don't have it now, you might have it tomorrow. So join us on Slack and ask your questions. And maybe Davide will be available in Gather like for 10-15 minutes after this. And you may just interact with him and ask questions if you have it there. So thank you for joining.
Thanks, everyone. Thank you for having me.
Thank
Take
you.
care.